Okay, so get this. A team of Chinese scientists just dropped a paper in Science Advances, and what they're claiming is, well, it's stunning. They think they may have solved one of the single biggest roadblocks keeping fusion power in the realm of science fiction. We're going to dive into this, because if this is for real, the finish line for what has been the dream of science for decades might be just around the corner. But first, let's just step back and ask the big question, the one that's driving this entire massive global effort. I mean, can you imagine a world with energy that's not just abundant and cheap, but also clean? Is that future actually possible? For as long as I can remember, the answer has always been this tantalizing maybe, all hanging on whether we could figure out how to build a star right here on Earth. So, what is this holy grail of energy we keep talking about? It's nuclear fusion, right? The very same process that's been powering our sun for billions and billions of years. Let's do a quick refresher on why humanity has been chasing this particular dream for so long. Now, don't get this mixed up with nuclear fission. That's what our current nuclear power plants do. They split heavy atoms apart. Fusion is the exact opposite. You take really light atoms, like forms of hydrogen, and you smash them together under incredible heat and pressure. And when they fuse, a truly immense amount of energy gets released. And the promise here, it's just on a completely different scale. The main fuel, deuterium, you can get it from plain old seawater, so it's basically inexhaustible and it's super cheap. It creates way less radioactive waste than fission, and the waste it does create is much less dangerous and easier to handle. Oh, and a meltdown? Not possible. It's pretty much the ultimate clean energy source. So if fusion is so perfect, what's the catch? Why don't we have it yet? Well, for decades, scientists have been running full speed into a wall. A massive, seemingly unbreakable wall that was holding the entire field back. That wall has a name, the Greenwald density limit. Here's the simple version. To get more power out than you put in, you need to pack a lot of fuel into your reactor. But every single time scientists tried to cram enough fuel in, the whole reaction would just fizzle out. The plasma, that super hot fuel, it would go unstable, and the fire would just die. And this quote from our source material really sets up the perfect analogy to understand this. Think about trying to cook a giant steak on a barbecue. This analogy just nails the problem. You need a lot of charcoal to get the grill hot enough, right? But if you pile on way too much at once, you literally choke the fire. It can't get enough oxygen, and it goes out before it even gets hot. In the fusion reactor, the plasma was the charcoal. Every time they added enough of it to cook the meat, the reaction would just smother itself. Game over. And I want to be really clear here. This wasn't some small technical glitch. This limit was considered a fundamental law of physics for these donut-shaped reactors called tokamaks. Even ITER, the massive multi-billion-euro international project, they designed their entire machine to work within this limit. They basically accepted it as an unbreakable rule. But what if you didn't have to accept that rule? What if you could just change the game completely? This is exactly where this Chinese team's revolutionary idea comes into play. You see, for years, the standard way to heat this fuel was to just run a massive electric current through it. The problem is, as the plasma gets hotter, that method gets super inefficient. It gets harder and harder to heat it, and the plasma starts to get wild and unruly. So this team tried something totally different. Right from the get-go, they blasted the fuel with ridiculously powerful microwave. And here's the second brilliant analogy from the source material. They didn't just invent a better, fancier match to light the charcoal. No, they threw the matches away and brought in a blowtorch. See, the microwaves don't care about resistance, they just directly shake the atoms themselves, heating the fuel way faster and with a ton more control. So, what happened when they used this blowtorch? This number right here, 1.65. They successfully crammed 1.65 times more fuel into that reactor than the Greenwald limit said was even possible, and the reaction didn't die. They didn't just push the limit, they blew right past it. So why is that one little number such a huge deal? Because if you can burn that much more fuel using the same amount of startup energy, you can finally reach the holy grail of fusion. You can get more energy out than you have to put in. And that is the absolute key to ever building a commercial power plant. Okay, so they broke the density limit. Problem solved. We can all go home, right? Well, not quite. Breaking that barrier created what seems like a whole new problem, but the real beauty of this solution is how it solved that one too. I mean, it's the logical next question, isn't it? If you have plasma that's way hotter and way denser, isn't that just going to act like a super-powered sandblaster on the inside of your multi-billion-dollar machine? This has always been a massive worry for making these reactors last long enough to be useful. And this is the most elegant part of the whole discovery. The microwave heating didn't just make the plasma denser, it made it better. It naturally focused the hottest part of the plasma right in the center, away from the walls. It made the whole thing calmer, less turbulent. And because it wasn't thrashing around so much, it wasn't slamming into the walls, which keeps the plasma pure and, you guessed it, protects the reactor. Just look at the data here. The difference is absolutely wild. The core is burning at up to 100 million degrees Celsius. That is hotter than the center of the sun. But the edge, right near the reactor wall, is a cool 1.2 million degrees. That incredible drop-off is exactly what saves the machine from destroying itself. So what this all boils down to is that this isn't just a lab curiosity. This double win, smashing the density limit while making the plasma calmer and safer for the reactor walls, is the thing that could finally make commercial fusion practical. It suggests these power plants could actually run for long stretches of time without needing to be rebuilt. Now, of course, this is one result from one lab. It has to be replicated, it has to be verified by other teams all over the world. But it's a fundamental shift in how we think we can control a star in a box. So it leaves us with this massive question. After all these decades of being just 20 years away, is the dream of clean, limitless fusion energy about to finally become our reality?